So today we will look actually at use of deep learning in NLP tasks, meaning natural language processing tasks. Do so, we will open, of course, our notebook in CodeSpace. Of course, learning properties. Basically, in other words, how to set up GPT at home, right? And again, of course, the technical part is not that difficult. The only real difficulty, of course, is getting the hardware, setting up the technical requirements, and coming up with reasonable parameters and having time to play around with those. So that's the biggest challenge. There's mostly data preparation tasks that will present problems. So deep learning for NLP, right? This one here. And we'll look at the history what led to this development, actually, right? So, some important papers I mentioned on last time, actually, right? So we discussed the core components, or what we need. Of course, we need to have some sort of grammar. Of course, we need semantics, meaning, right? And so we need to do the semantic analysis. We, of course, tokenize. We talked about normalization. Also, we talk about embeddings, right? The idea, of course, is that we represent words as vectors, basically. Each word or each token, again, it could be a word, it could be a sentence, it could be a whole document, but underneath we represent them as some sort of vectors. So this is what we call about embeddings. Word embeddings, text embeddings, sentence embeddings, all kinds of embeddings. So that's what we talk. It all means really, it's a fancy way of saying that each token gets a numerical vector assigned to it, right? What kind of vector, right? That is a really wide field open. We saw this bag of words, right? You can make a vector of, say, first item represents a count of word A, second would be a token of, say, B, third would be maybe, I don't know, car, right? You know, and so on, fourth would be dog, and so on and so on, right? It would be a bag of words representation, right? But without any sort of context within, right? But we'll see, of course, for more improvement, the big gains have come from embeddings that somehow represent the context, right? Again, words without their surrounding words are pretty much meaningless, right? Again, we talk about these examples like bow or duck, words with multiple meanings that have you need the context. You need the context in any language, basically, right? So word embeddings, right? So there, it's a way to represent words as dense vectors. Dense. What's the word dense here? This means that. What does it mean? Dense, density, dense vector on sparse vector.
Lot of dimensions.
Yeah. Okay. You have all the dimensions. That's not all, but those dimensions are actually filled in. Right? You have some values for those. When we talk about sparse vectors, right? We could build a sparse vector, let's say, a bag of words model. We have our language, let's say Latvian language, 300,000 different words, right? On our sentence, it will be extremely sparse because we'll have maybe, six words present in that sentence, right? The rest will be zeros, null, whatever you want to represent. It will be basically very, very sparse. And the issue with sparse vectors is many algorithms don't really work well with sparse vectors, right? So you want dense, full of data, full of non-zero values. Obviously, zero has some value. Maybe let me close the door so my loud voice or colleagues don't really get scared. Maybe I start talking, get excited about dense vectors. Oh, they actually are pretty. Yeah. By the way, I should mention that already in the back room, if you notice, there's a computer which is begging for action. It has a nice 4090 video card and has some RAM. It's something we set up last year. But if your bachelor's next year needs, it's waiting there to be used, basically, right? So you obviously, yeah, you can't take it home, right? You have to come up with a project. If you want to play games, of course, you need some sort of project or thesis that requires playing games, right? Yes, so, and then it's not so much fun. Okay, yes. So word embeddings. right? So board things are extremely effective for a broad range of tasks, right? So idea is, of course, you can create different embeddings. It's extremely wide open field, right? And a very important paper was this Word paper. This came from Google. Let me open up this paper, right? Jeff Dean. This is like the best programmer on Google, basically. It's like the Chuck Norris of programming, basically. Right? There are jokes about Jeffrey Dean's programming, basically. Right. So he's one of the core contributors to this algorithm, right? And of course, Thomas Niccolo, Kai Chandler, they all, of course, are equally important, actually, right? So he's probably more of a supervisor here, right? So, and basically what it is, you feed it in words or sentences, and you get the outcome vectors. And if you have vectors, what can you do with vectors? You can compare them. Right. And what kind of comparisons can we do? Right, we'll talk about this in a moment. Right? We'll see about this in a moment. So, there is, in fact, I don't have here added that very quickly, right? So basically, there's a library called Jetsim. I'll show you this guy from Czechoslovakia, right? Radin, right? Topic model for humans. He has written algorithms for this to play around with these models. It's extremely simple. If you know a little bit of Python, you just basically import the library, right? Import Word to Vec, and you generate a model. You can train it. If you have time, maybe I'll come back to this and show you how easy it is. And then multiple times, right? And what do you do with this actually, right? You can compare. You have these embeddings. The bad news is you don't know what they mean, right? It's just numbers, right? It's just like 100 dimensions, 1,000 dimensions of numbers, right? But the best thing is you can do is you can compare. Maybe let me go back to the paper. Let's see if I can show you what's in the paper. You've probably seen this somewhere, right? It's not a long paper, but basically the king and queen, right? That's also how the neural network is done. But basically, right, you can do relationships like word pair tasks, right? Athens is to Greece as Oslo is to Norway. These type of tasks, right? Astana is to Kazakhstan as Harare to Zimbabwe, right? Apparently, Harare is the answer to the Zimbabwean capital, is it? I don't know. Apparently it is, right? So, Chicago, Illinois, Stockton, California, right? City and state, right? These are not simple tasks, of course. So, of course, man, woman, brother, sister, grandson, granddaughter, right? Similar relationships, basically. Why does this work? Because brother and sister are used in similar context. Same goes for grandson and granddaughter, right? You feed enough amount of data, you will see this vector embedding, right? It will, we can call it learn, right? There will be these weights, these vectors. There will be some representation that grandson and granddaughter really are used in a similar context. And then, how do we compare? There's multiple ways. How do we, if you have 100 vectors, two vectors, 100 numbers, 100 floating point numbers. How do you compare them? Well, you could do Euclidean distance, right? You could see how far they are from each other, right? That's one way. But there's something called cosine similarity, right? And if you take a linear algebra, I think you might talk about this, right? But it turns out cosine similarity is very easy to calculate, even it's fast way of calculating. You calculate the angle. I'll show you what it looks like. You may have not seen it. Cosine similarity. It's probably what a lot of new databases use this so-called vector database, cosine similarity, right? I'll show you, right? So here, let's see it here. So basic idea is very simple, right? Instead of measuring distance, we get a picture. Come on, where's the picture? No picture here. That's useless. Sorry, Wikipedia, you failed. Right, science direct might be better. There's a lot of papers. This is a huge field of research. But the whole point is that cosine similarity. Basically, we are measuring angles. Not for geeks, okay. We are measuring angles. Yeah. So basically, instead of measuring distance, 5x, we are measuring an angle. And this angle actually can represent some sort of relationship. So meaning, if you have angle 0, right? This means these words behind the embeddings, they are probably used in extremely similar context, right? Again, if you think about it, if you have similar angle, right? It does not mean that they're actually in the same space, right? It could be really far away, actually, right? It's just the direction is same, right? They could be very far away, actually, as far as this space, like yx could be very far away. It could be somewhere here, right? Nice ads, right? So the angle is actually important. So there are many uses for it. Also, there are cases where this doesn't work so well, actually. So that's one of the main things what's happening these days is this cosine similarity is widely used. And there's reason also why it's so used is because it is quick to calculate even if you have a lot of these vectors. If you have thousands of tens of thousands, by some linear algebra tricks, you can calculate very quickly. Euclidean distance is actually, if you have 1,000 by 1,000, you need distance from everything, right? It's actually, it turns out it's kind of pain to calculate, and it does not scale so well. So that's one issue, right? So we'll see about that. So board embeddings can effectively represent individual boards, right? So, but of course, again, for these tasks, for similarity tasks, these are great, right? But of course, sequences of boards, of course, influence meaning, right? So for more more difficult tasks, right? Well, we need something a little bit deeper, so to say. Deeper, right? So something called recurrent neural networks would be one of the solutions, right? Meaning they represent the sequential nature of our language, right? I'm speaking, when I'm saying something, right? Your brains are also building some expectation what I'm going to say next, right? If I say red, I might say blue next, maybe, right? If I say nurse, I'll say hospital next, maybe, right, and so on. If I say student, grade, and maybe I'll say bad grade, right? You expect that I'm probably talking about you. You build some expectations, right? So, right? It happens like that, right? And somebody starts talking, and you build a mental model, right? Your brain, even if you don't want to do it, your brains do the same thing, right? So we can, referring a pronoun like who is he? Is it Miguel or is it Eduardo in some sentence, for example? Right. So language models are, after all, they're just probabilistic models that predict the next word in the sequence. That's basically all. We've used them for some fancy things, GPT-4, right? Just came out with nice new image model. But underneath, right? We'll talk about computer vision in the next lecture today. But underneath, we're just generating next token based on some context, right? So there are a lot of similarities still with the stupid, simple Markov chain models, actually, right? It's just that the context is much bigger, right? And we sort of say no, or probabilities for next token are influenced by a larger chain of previous tokens, right? So embedding vector, right? So there's some hidden state, right? So theoretically, these networks can remember information indefinitely through the hidden states. By the way, if you talk about these large language models, you can think of them also as a way of compressing knowledge, basically. It's like a lossy way of compressing our knowledge, or human knowledge, right, in some form, right? It's not perfectly reproducible, but we sort of get a rough idea. And the more we train, the more data we have, the larger the models get, theoretically we can compress more knowledge, right? So we can apply these RNNs. So we need to, of course, still need training, right? And I think the book mentions some improvements. So one of the improvements, of course, is something called long short-term memory. It's a network I've used before myself quite a bit, actually, for OCR tasks, for recognizing written, for recognizing text in images, right? So it's an advanced variant of RNN. So basic idea is that long short-term memory, there are some mechanisms inside the neural networks that remember for a longer time, tend to retain the knowledge longer. So meaning you saw a letter A, maybe 100 training data rows later, you see this letter A again, there will be a way of activating this, I'll call this memory, basically, right? Let's see if we have any pictures of this, right? So there is also another thing, right? We can do something called sequence models, right? We use two neural networks, right? Two is better than one, right? So a big improvement. And then we come to attention. And again, I mentioned this paper, right? This paper, attention is all you need. Attention is all you need. Attention is all you need paper, right? So this is what is like probably the most cited paper of last 10 years as far as machine learning, as far as NLP, as far as anything dealing with deep learning, extremely influential, right? They mentioned these guys here, right? So we can review the paper, right? There might be a picture here somewhere. Right. Well, this is actually the neural network right here. Activization, right? The famous or infamous transformer architecture, basically. Right. We have some inputs, basically, right? We do embedding, right? We have to, of course, do embedding. So embedding, I know this means we generate some numerical representation. What we're adding, we never add letters, right, or words. We add their numerical representation, right? And then there basically is this the transformer step, right? At the end, right, we have output the probabilities, right? And we have outputs, right? And we basically you get the next token, right? So very interesting. So basically two steps: encoder, decoder. Again, so attention function is like a basically, how should I say, they're all vectors, right? And again, we call them attention, something that's important, something that you should pay attention to, right? So there's some math described. I really recommend you read this paper in more detail if you want to see this. But again, obviously, you don't have to read it to implement the network yourself, right? Karpati, if you have seen his videos, you can put the GPT-2 type of network, the state of art from like 4 or 5 years ago, on a normal, video card, or if you're renting a small, tiny, cloud-based center from Google Colab, you can build a small network. And again, you'll be able to generate some texts, but obviously they won't be nowhere good as the state of the art, because the state of art has been moving last 3-4 years, has been really advancing, and mostly just by feeding in more data, right? Really hungry. These AI bots are really hungry, right? They try to get more data, right? Cleaner, right? So, again, we have our tokens, right? So, attention, right? So, basically, this transfer model, it captures both long distance and nearby context more effectively, right? So that's there's something called attention score, right? So whether basically that previous token is actually important to this current token. So another thing you might come across is something called pre-training, right? So you need oftentimes you need some data with some answers, right? Well, what you do is you can do a little bit of faking, right? You can basically you have all the labeled data, right? So you want to leverage this unlabeled data without any answers, but it is right into to use it, right? So basically one way of doing this is basically pre-training is a way of called transfer learning. We have a model, right? And we just train on general concepts, something we already have, and we can add our existing this unlabeled data, so we can use it also in building our models, right? So this is basically sort of like challenge of data scarcity, because again, we have an issue, of course, we need as much data as possible, right? But ideally, it's be all labeled nicely. Now, pre-trained word embeddings, right? So, the globe, I won't talk too much about global network, it's extremely similar to Word2Vec actually, as far as it works, right? We get the embeddings, there's other embedding models, right? So, another very cool thing is math language models, basically, right? So the RNN and LTSM models, they are sort of based on previous words. But masked language models, idea is this. We basically we have a sentence, we have some document, we take away a word, and we sort of try to predict what the word should have been. So basically, we only have the answer, right? We pretend we don't know what it is, and we make the model guess what that word should be based on some certain window, right? Maybe, I don't know, 10, 100, long context. And so we can, in effect, bypass this pre-training step. We don't need the labels. We're just given a whole bunch of text, and for each word in our documents, in our billions of documents, we are trying to guess what that short word should be, and then we check. So this allows us to train the model, because we know the answer for each position, right? But we just take it away, we mask it, and then we make the computer, make the model guess it. It's kind of cool approach. On the bear, you see here, this example. So the river, right? River rose 5 feet, right? What else could there be? The river was 5 feet? No. The river stunk? No. The river left 5 feet? No. So rose actually, even though rose we know is a flower. In this case, it actually accurately represents. I don't even know if there any other word could be or human brain. Is there anything else we could include here? You can ask ChatGPT right now, right? What it should be, right? So the river rose 5 feet. I don't think you could put anything else in there. Is there anything else we could put which makes sense as far as English goes? The river 5 feet. Dropped 5 feet. Yeah, that would be alternative, the antonym, right? That would be an option. Drop this rose 5 feet. So
maybe like moved,
maybe, yeah. Like widened, but then you have the two words, widened by 5 feet, right? I think you said it shrunk. No. So rose 5 feet is one of the answers. So obviously, you run this through model, assuming you have normal English language, and it's not all slang or something, right? Which is, of course, the issue now, right? There's a problem, of course, these newer models that are all now trying to learn. They are being trained on a lot of garbage data, so they learn a lot of bad patterns, right? So but this is really cool approach. So it's called bidirectional, and I don't know if I mentioned this. It's called BERT, like Bernie, I see BERT, right? So BERT model. I don't know if I have it here. I have it. So BERT is booked in 2020. There's only GPT-2 was available internally. They do a lot, of course. So BERT model, BERT Google, right? Yeah. So this was another big influential paper, and this came before GPT. This actually had a whole Jacob Delin, right? 2019. So this is just before GPT. So this is very promising. There's one problem with the BERT, and again, it is practical issue. Turns out BERT is harder. It's computationally harder to train, actually, right? We have BERT actually at the NLP lab at the A lab in Latin University, or colleagues actually, right? And it is hard to train, basically. That's why GPT, the transformer model, is kind of born out. BERT is sort of on Robert, and there's variations, improvements in this BERT model. It's very promising. It can do some things quite well, actually better than a GPT. But the issue is, nobody, as far as we know, has trained BERT on the amount of data we have used for transformers. Because transformers have taken off because they're good enough. They do this. They have these big improvements, and they're easy to train. And basically, there are some technical improvements made for training transformers, which made training on these NVIDIA hardware extremely easy, right? So that's one big issue. It's not technical, it's like a pragmatic issue. Yeah, we can throw a lot of hardware, it's easy. I say easy, of course, in quotes, right? You still need a team of people working on it, of course, you need a lot of money, but it is not hard to do this scaling conceptually, right? You just throw more money in it, right? For now, I think the next model probably of GPT-5 will be probably a couple $1 billion, right? You heard about the OpenAI is raising $40 billion now. Problem.
For what are they raising?
Well, they wanted a trillion, remember, right? They want a trillion. They're raising 40 billion at a 300 billion valuation. We said, well, for what? They're getting 3 billion from us, right? But it's costing them 9 billion every year. It's the Uber type of approach to startups, right? They're losing a lot of money. Well, you could say they wouldn't be losing so much money if they were not training so much, right? If they just stopped, right? They would probably be making money, right? But they're trying to advance. So it's like an arms race, right? So they want a big war chest so they can, they're afraid, of DeepSeek, of Google, of course, of Facebook and so on, right? So it's who gets the most success training, right? So Google, of course, is doing pretty well, actually, right? Yeah. So BERT is very nice, right? There are all kinds of. It's very conceptually simple. Again, I told you about this masking. So bidirectional encoded representation, right? So it conditions on left side and right side of your text. So again, we saw this example. You have some missing words. You keep adding. You keep taking off words from your text, and you try to guess where it is, and that's how you train your model. Very simple idea. Very simple idea, right? But again, if somebody could come up with a more computationally easier way of training it, right? Maybe BERT could actually be a big improvement, right? So because when I tried to train BERT on a Google Cloud instance, and well, it worked. This is like a couple of years ago, 3 years ago. But it was not very useful yet, because it just weak hardware and also not enough data, right? So yeah, so the field, of course, NLP, we have GPT-4, right? GPT-4.5, right? All of these, not should add, as well, of course. DeepSeek, of course, right? So what's the big hotness right now? DeepSeek, right? Let me add this, it'll make it. Let's see if it's going to add. Let me see if it's going to add DeepSeek. Is GPT going to talk about DeepSeek? Let's see. Is it? No. It doesn't know. It has no. It's not. DeepSeek is only came recently. No, by DeepMind. Okay. DeepSeeker, not DeepSeek, right? Yeah, DeepSeek, right? Right. Where Google guys saw this already, right? So transform model. So that's the same one. 45. So what's new hotness? 2005. To me, cloud. Of course, I mentioned cloud here. The cloud, of course, is cloud for coding. Cloud for coding is the best. But what I should mention, what's the new idea? This book doesn't have this at all. But this idea of what you have probably, you have paid attention to this. It's called chain of thought. Chain of thought models, meaning reasoning models. Now, again, reasoning involves, it's not really reasoning as we humans do, but the idea is to keep adding prompts, sort of like to make the model explain itself, basically, right? So they are the ones who are producing some real improvements. So 2025 trend in 2005, trends in 2025, chain of thought models. Come on. Models, right? These include, right, we have, of course, GPT, what is it, 3? No,
3 and
3, what's it called? 0?
No, 03.
03, yeah.
And 012.
012.
No, like as
Oh,
well. 03 and 01. They have two reasoning models.
oh, 03, yeah. And then, okay, let me go to my friend over the computer, right? Let's see exactly. AI, right? Let me see the models, right? You can see again, chain of thought, right? Again, I use this a lot, right? Category. We have a series, right? GPT, right? O1 Pro, right?
Yes.
Right. So for reasoning, right? So they think harder. This means there's more prompts. Essentially, of course, it's a party trick in a way, right? If you're cynical, well, again, you can be cynical, but produce results. But basically, it's a prompt. You get some results, and using the prompt, you sort of build on that, and you build on that, and you build on that, basically, right? So there's some ideas. Very, very cool, right? So It's very expensive now, right? The Pro is expensive. It's the new one. It actually used to cost $200 a month, right, to use, right? Now you can pay for it by piece, right? So, use the links here.
Can you run a prompt there?
Yeah, I can, but I don't have API key on this computer, right? Yeah. If you're gonna give me your API key, I will. Yeah. No. So I will. Yeah. So which one else? DeepSeek has one too, right? Claude has one too, not Sonnet. Reasoning is very general.
Yeah, Claude Sonnet with the reasoning.
Yeah.
Sonnet thinking.
Yeah, it's in this one here.
Yes.
Right, so this one. Again, cheaper, but also pretty expensive. Claude's also pretty expensive. Again, the thing is, what's interesting is the cost also becomes important. Mistral, let me see here, go back. I used to have different thinking reasoning models. Providers, more, okay, so Gemini has one, DeepSeek has one. Which one?
Grok.
Grok, of course. Who owns Grok?
Elon Musk.
Yeah, Elon, yeah. I don't trust him with my tokens. So, DeepSeek reasoning model, mixture of experts. So, another thing is, another trend, this is like actually 2023 trend, it's still around, still used, of course. It's just an important thing, it's called mixture of experts. So, instead of you don't have one model, you sort of have a fight of models, you have multiple models underneath. You do your prompt, right? You have a multiplex models for different subfields, basically. So you need, of course, some sort of way of saying, okay, which prompt do you want to use? Which answer do you want to use? Do you want to answer the coding question, or language translation, or maybe some sort of reasoning, right? So on and so on. So it's not as simple as that, but that's the basic idea. So they have the reasoning model too, right? R1, right? Yeah. So this is reasoning model. Yeah. O1 was, of course, original one, right? And you could run DeepSeek on your own server if you want. It will be slow, right?
Really big server.
Yes. Yes. You need only like 500 gigs of RAM. No big deal, right? Yeah. That computer has current 28, by the way. Right? Again, do you know what the issue with using RAM is? Of course, what's the big issue with RAM? It's again technical issue. Lots of these things are technical. You can basically run lots of models. If you have access to these weights, you can run them. The issue is what? You have the RAM, right, 500 gigs, but the issue is token generation speed, tokens per second. It's slow, right? I run some pretty big models just for fun on just a regular server without the hardware GPU. So that's why GPUs are used. Why? Not only because they have good, lots of computing units, but also because the RAM, the type of memory used in graphical cards, has much higher bandwidth, which is a physical thing. It's transfer speed. So for those who have Macs, well, anybody has Mac?
Yeah, I have.
So how much RAM do you have? No more Mac users here? No. Okay, yeah, so while you're checking, so the idea is, of course, Mac architecture lets you share the so-called unified memory. The way it works, it gives you higher bandwidth. Not as good as video cards, right? Because the issue with video cards is that your consumer level ones, the highest is now 32 gigs, that one is 24 gigs, right? And it's not really enough to run big models. What is one of the tricks we use to run big models with not enough memory? What do we do? The weights are floating point numbers, right? Originally, right? And when you say, okay, you have 70 billion parameters, right? Well, if each parameter takes 2 bytes, anyway, so no. So not locally. But the good news that those computers, the Macs there have a lot of RAM. I asked for more. I think we have 96 gig model, right? One of those things have pretty a lot of RAM actually. So I was saying the RAM, the speed. So you have 70 billion parameter model. As it came from factory, from training, right? you need at least 140 gigabytes of RAM, roughly, right? So what people do is something called quantization. Basically, the idea is this: you squeeze in, you have float, and you transfer it to it like a 3-bit or 4-bit value. Meaning, what does it mean, 4-bit value? This means each weight is only values from what? From 0 to 15, 4 bits, right? 2 to the 4 is 16, right? So 4 bits, you can go from 0 to 16. You see, okay, does this actually help? Does this actually work? Well, you do lose, so the models are not as good, but you still gain a large percentage of performance. And but you can run them locally and faster, right? You don't need as much memory. So this is one of those trade-offs, right? Practical things, again. So if you see quantification, quantified models, this means they have been sort of compressed, right? And then people have discovered, you see 3-bit models, right? That means the only values are from 0 to 7, and those sort of like the weights, they come kind of not so good anymore, right? Like 4 or 5-bit models actually are pretty decent. And there are people who specialize in this. There's a place called Hugging Face, right? Where you can see these models, right? And in fact, the process is pretty simple, right? You define your floating point value in sort of like 16 areas, right? And you assign each area to that particular 4-bit value, and that's it, right? Simple. Again, so it's a lot of technical things now. So, also, previous, right? Mixture experts models. One of the ideas. Let's see so combine different architectures. So basically by combining multiple, right? So that was interesting. So that's sort of like the sort of trends, right? And again, some issues, right? Some practical issues. So practical issues are practical issues. Learning models. Totally. You need memory. High amount of right. So training, of course, right? So what the issue is, of course, is the only way to train them practically speaking is to use NVIDIA hardware. You have these nice little boxes. Essentially, they're using the same chips as far as GPU, graphical processing units, as in our gaming cards. But the way they're built is actually they have access to much more memory and also a way of chaining these computing units together. So they might have 80 gigabytes, for example, right? But you can chain together, maybe use 10 of them, right? You get 800 gigabytes roughly, right? Then you could run your DeepSeek 700 billion parameter model. However, of course, problem is one of these racks cost now the price is ridiculous. I think from 30,000 or so, roughly one of them, right? And how many racks did Facebook buy? How many 800 racks Facebook has 600,000 equivalents by 2004, right? So that is what? 600,000 times 30,000. We do the math, so that's what? Times 30 would be 1.8. No, sorry, 30. No, that's 18 billion. So Facebook is spending about 20 billion on NVIDIA hardware, roughly, right? So the huge, billions, literally billions. Right? And of course, that's equivalent, right? So he only has 100,000, right? Right, but it's probably buying more. Yes, that's cash, right? So now, so when 150,000, right? Yeah, that's good. But this is a joke, right? Not for 12 each, right? Yeah. This is a joke, right? So, 500,000, of course, right? So they sold 500,000 Meta, right? Also, of course, who else buys them? Of course, Microsoft, because OpenAI is using Microsoft computing centers, right? So, of course, these prices, you might say, okay, why is not AMD doing anything? Why are not people, these expensive companies, why aren't they building their own chips, right, to do this? Well, it's not so easy. I mean, yes, there are alternatives, but for this large-scale training tasks, it is NVIDIA still has this huge moat, this business moat, because it's all that sort of ecosystem is there, and you just throw more money at it and it works, right? The other things like AMD or Intel, of course, or other your own custom chips, they require a lot more setup and much more expensive. You're not sure it's going to work, practically speaking. But now about you, right? There's interesting development, right? Again, so Macs and Macintoshes on something called AMD, I think Rix AI, I think it's called, what's Rogue AI? What's the name of it? It's a new thing. These machines are very interesting. Macintosh for local models. For models. Which one?
Radian.
I'll give you the link. So framework, if you know this called framework company, I'll show you what I talk about. Framework company, right? Actually, you can buy them in Latvia now too, right? But they introduced, right, this stuff. So it's kind of interesting. You probably know what framework is, right? It's a startup, like 5 years ago, 6 years ago, they make repairable laptops. But now they made this kind of pivot, business pivot, and they made it more sideline because they realize how important this thing is. A framework desktop, small machine, right? Tiny machine, you can pre-order it, learn more, right? So what it is basically alternative to buying a Macintosh with a lot of memory, basically. It costs 2,000, right? It's probably all sold out, I'm sure, right? But the idea is this, that, right? The CPU is not important, right? You want this, right? You don't want the 32 gigs, right? No, you don't care about that. It's only, 1,200 euros, right? You don't gain much. Then you might as well buy a GPU with that, right? This one's not good, but this one is the one, right? Is what you want, really. If you want to run models. So idea is that this machine, right? Again, just purely because of the way memory works on this machine. That's all what really it is. So for 2,000, well, it used to be 2,000, now I guess that it's now 2,000, 2,400 euros, right? You get this little machine, so you can run models up to like 90 billion parameters size, roughly, right? 128, it's non-upgradable, right? So in a way, this company, this framework, they kind of like, I wouldn't say betrayal, but they kind of went away from the mission. They saw this machine, right? This idea that they could build this very, very powerful machine for a sole task of running local models. So if you need to run local models, so this looks like the machine to beat. Of course, question is how many they will build. It's not sold out till autumn, right? So you'll see how good they are. Because the big question is token speed per second, right? How many tokens can you push out? And again, we've seen this is very important actually, right? Because again, you can run this, if you have 128 gigabytes, we can run these models on our machine, right, on regular RAM, but they will be slow, meaning 2-3 tokens a second, you really can't do anything, really. That's not really, usable, right? So this is very, very promising, right? So very interesting. I'll add a link to this actually. What they call so it's using this this is AMD architecture actually, right? Let me see here for the details. All right, so standard AP. So AI Max. They call it Ryzen AI Max, basically, right? Yeah, it's kind of really silly name. Really silly name. It's a stupid name. Because the AMD is horrible about this. They have these really strange naming conventions, right? So it's CPU and GPU together. It's integrated, basically, right? So again, it's really not that amazing a computer just for general tasks, but it promises to be very good just for running these models, these large language models, basically, right? So I mean, it's good. It's going to be a good computer, but of course, you don't buy it for gaming, right? But just for these models, so this is going to be, right? So we'll see. Maybe some of you have ordered, right, already, right? Yeah, no, not yet. Okay, let's go. Horizon alternative to Macintosh, AMD, the stupid name. No, it's called, because Ryzen, of course, is CPU, of course. In general, right, some of you may be running Ryzen with CPUs in general, but Max plus 395, Ryzen Max plus Ryzen Max, it's going to be notice, Max plus 395. Bad name, good shared CPU, GPU architecture. Again, and so crucial part is RAM. So one big downside of all this hardware-wise development is that the memory has to be soldered. You can't upgrade, and that I think is a big loss actually, right? So it's either you want fast memory, then you don't get upgradability, right? It's also that we're running into some technical issues, real issues. It's mostly all this progress is not mostly the or thinking part. It's actually these hardware issues. Okay, all right. So yeah, so there's a whole bunch of papers, right? So Albert Bohr. So there's all kinds of BERT-based models, right? So attention paper, right? So, and again, most of these books I would say not really that useful, but I mentioned, I think, Carpenter, of course, three blue, one brown. That's a good video. You probably know three blue, one brown, right? Yes, right. He has an act, and of course, this guy Andrei Karpathy. He worked at OpenAI, I believe. He left for his own startup, right? He has this video, right? In a couple of hours, you can build your own GPT, basically. But again, it's good for learning, sort of see what's happening. But again, you're not going to get any good results unless you have like a rack of machines to train it, right? You know, 500,000 horse of machines, or you rent it. You can rent it for a couple $100,000. No, you can rent for a couple $1,000, right? If you're smart about it, right? But the problem is if you do something wrong, right? You just lost a lot of money for nothing, right? Your model doesn't work really, right? So again, good stuff here basically from zero to hero. This is also good, right?
Can't you train it on cloud, and the cloud the prices are fairly cheap?
Yeah, no, that's what I'm saying. So this is the interesting moment is that. That's what I was talking. You could train a pretty good model for a couple $1,000s, right? On a cloud, right? Meaning you can rent the machines now, right? Yeah, I can show you some rent companies like rent H100, right? Data crunch, no, waste AI, right? So do the math, right? This is one of the leaders, right? So look at this here, right? Oh, price has gone up. So you rent 4 of them. So what does it mean? So you rent 4 of them. That should be 80 gigabytes times dollars. I don't know. Right. So you should have 380 gigabytes. One machine is 80 gigabytes, right? You should be able to access 32 per GPU RAM. So it's 4 times 80 is 320 gigabytes. There's a way of interconnecting them. So you train a pretty large model for $8 an hour, right? So one day is about 150, about $200, right? So you need to probably train for a week, 2 weeks. That's what I said, a couple $1,000, and you can get pretty good models, like GPT-3 level, basically, on your own. And of course, why would you want to do this, of course? Well, in general, you want to do this if you have some specific clean data set, which you don't want anybody else to use, basically, right? And you maybe have some weights already, right? You want to do something additional training, right? Yeah, right. So this is, of course, the way, what's happened is in the last few months, last 6 months, there's been a little bit of crash in this price, meaning there's only 2 types of players now, basically. Only these big companies which buy thousands of these expensive cards, and people like us, who want to just run the models locally. We don't do the training. We do very little training, actually, right? We do it, it's very cheap. And the idea was that people would be running these mid-sized companies would be also training these type of models. And it turns out not many of them are doing that as much. I mean, they're still doing it, right? But I guess they're not getting really good results. Because either you go big, right, or you go home, basically, right? Two ways, right, basically, right? So, but yeah, if you want to play around, it's not so hard set up, actually, right? You can rent four or five nights, right? But okay, the issue with these environments, this is much harder, right? This is just a graphic card, right? You basically almost can't buy it, right? But the issue is the interconnections are kind of hard, right? So yeah, I'll mention this here. Well, rental. Yeah, so rental.
You ever rented?
Yeah, I've rented it before, but again, I've not done really big. I mean, I don't want to spend thousands of euros on. I would probably need to. Well, we have our local computing, supercomputing resource, Riga Technical University, right? We're part of Riga Technical University, right? But there's a big line of people waiting to use it, basically, right? It's a queue-based system, right? So you need to have something very promising, right? And of course,
also rent it for training.
you mean?
Did you also rent it for training?
Yeah, I did for training on here also, but I didn't really get anything useful, right? So I mean, it worked, but So
did you also purchase for more than 1,000?
No. That's a problem. That's the issue, right? So and that's I think the issue. Many of these small, mid-sized companies are running into. They're getting some results, right? But these big models are so much better. You say, okay, why? So you do the math. What do I gain by doing this? It's kind of fun, of course, right? But the difference, right, in the budget is so large. Of course, as we know, DeepSeek, well, they didn't do it for a couple thousand. The budget, well, you don't know exactly how much is spent, but for the success, for the level they did, right? They took some existing models like the Llama and everything, right? They did the tricks, of course, right? You don't know all the tricks, but they spent relatively little. I think a couple million, right? That's relatively little these days, right? To get a top level performance, basically. So that's one of the things. Okay, so cloud-based rental of GPUs. Yeah, Google. I don't know. Google also rents Google Colab. Well, free. Google free. You can play around. It's free or low cost, right? Expensive. Right. Latest and greatest. Latest and greatest. Greatest. Come on. I got greatest. I think I have a Python code. That's why I can change the style. That's why. Yeah, yep. But expensive. A little paper space, right, of course. And of course, Hugging Space, of course, in general, right? Some resources, Hugging Face in space. Hugging Face. I recommend maybe account that Hugging Face offers many rebuilt models. Yeah. So they also have some good cool libraries. On the site. I think it's correct. Let's double check. So most people who do this is sort of like the place to be, basically. We have a code there as well, right? You can see what's happening there. Sort of most of the interesting stuff happening here for small scale models comes from here, basically. Okay. All right, so this gives you sort of like a big picture overview, right? If you want to get deeper, of course, we will. There's opportunity for that here as well, right? Get maybe part of your bachelor's thesis or something. Possibility. A lot of things. So again, so your opportunities will be, of course, in adjusting, fine-tuning some existing model, or possibly maybe doing some custom models on your own, basically, right? Or of course, as many people do, of course, the easy way is to sort of use existing model and adjust it or adapt it to some specific task, basically, make it a wrapper, right? We call them, of course, RAGs, right? RAGs, right? So, okay. So I'll see you guys on Monday. Everyone.
No.
Ministry of Economics to present their their website for the Glad Bible.
No.